Now let's look at a few situations. This situation here, where the curve is like this. So here we have a local minimum, and here the derivative is negative, whereas here it's positive, and here it's equal to 0 at the turning point, and it's concave up. So basically the second derivative is positive. Whereas we can have another situation which is like this, where we have a curve which is concave down, and here we have a local maximum, and here we have f prime of x which is positive, whereas here f prime of x is negative, and f, because because the derivative keeps decreasing, well, that means that the second derivative must be negative. Now there are other possible situations, such as this one. Here we have a function which increases and then it flats and then re-increase again. So at that point here the derivative is 0, but here it's positive, and here it's positive again. Right. This point, this specific point here, it's called an inflection point. So as a difference with a local minimum or local maximum, here the sign of the derivative doesn't change. It was positive and it becomes 0, and then it's positive again. But basically, because the derivative is positive, but decreases up to that point. See, because the slope here is more than the slope here. And here there is the slope here is less than the slope here. So the derivative decrease, arrive to 0, and then re-increase again. Well, at that particular point, f2 prime is equal to 0. So if f2 prime is equal to 0 and the sign of the derivative doesn't change, of the first derivative does not change, then we have an inflection point. Example. Sorry, I'm just going to come back to that. Actually, this first derivative doesn't have to be equal to 0. It could also be in the situation like this, where, okay, so kind of like that, and here f prime is different of 0, but you can see that f prime, which was the slope here, decreases, reaches the minimum here, and then re-increases again. Well, again, we are going to have f2 prime equals 0 at that particular point, and also it's called also an inflection point. So my mistake, f prime does not have to be equal to 0. Right, let's consider, for example, f of x equal 2x power of 4 minus x plus 1. And we want to find, 1, the turning points, 2, the inflection points. So, okay, turning points. So first, the derivative is what? 8x cubed minus 1. So f prime of x equals 0 when 8x cubed minus 1 equals 0, which is equivalent to x cubed is equal to 1 over 8. So that means that x is equal to 1/2. Right, so that's when we have a turning point, and at that point f of 1/2 is equal to 2 times 1/2 power of 4 minus 1/2 plus 1, which is equal to so 1/8 plus 1/2, 1/8 plus 1/2, which is 5/8. So okay, so that means that the turning point is at 1/2, 5/8. Okay, so now the inflection point, f2 prime. f2 prime, well, that's the derivative of the first derivative, so that's 24x squared. So f2 prime of x equals 0 when x is equal to 0. And right, so and at x equals 0, f of 0 is equal to 1, so there must be an inflection point at 0, 1 inflection point. Okay, so what does it look like? It looks like 1/2, 5/8, 5/8, 1/2, and then the equation point is 0, 1, which is up there. Yes, and so it looks so here it's come from there, so it must be a local minimum, so it must be like that. And yes, they're coming up that way. That's what the graph must look like.